So we have local data sets, which could be generated by a variable or a smartphone or by a weather station. And we learn a local model, and this local model is a linear model. So we learn the weight vector or the parameter vector of a linear method. And then you get nice bounds in the lecture notes that tell you how far is the learned parameters away from a true underlying parameter. So we get all kinds of upper bounds. I provide you some upper bounds. And in these upper bounds, how does the local data set enter these upper bounds in the analysis? So these local data sets, they consist of pairs of feature vectors. So here, this is the ith data set. Let's say this is the first data point. And then we have a label. ith data set, first data point, this is the label. And we can stack the feature vectors into a matrix, into a single matrix, which I call the feature matrix at the ith data set. Okay. And in many of these bounds, you see not the data points themselves, but you see properties of these products of the feature matrix. So you see feature matrix of the ith data set transposed times xi. And I used to denote these matrices using the letter Q. This is this matrix Qi. It's a quadratic, the product or a quadratic form of the feature matrices, so to say. So in these bounds, in all this analysis, the local data sets enter via properties of these matrices. And do you remember what type of properties enter into the bounds, into the analysis? Is it the shape of the matrix? Yeah, okay, the shape is the number of features. It has also a role, but what are the characteristics of these features that enter into these bounds? What did I tell you in the beginning, in the first few lectures? What is the most useful result in linear algebra in the whole course? Because this is a positive semi-definite matrix, as you can easily show. So it's also symmetric, so it's symmetric and positive semi-definite. And what can we do with a positive semi-definite matrix always? We can decompose it. We can decompose it into spectral components. So we have a spectral decomposition. So the spectrum, which is another word for the values of the eigenvalues. The eigenvalues are the important thing. So the eigenvalues of this matrix, the lambdas, the eigenvalues of this matrix, they define or they enter into the upper bounds, into the analysis. They enter into the characterization of convergence speed, so into the computational properties of the federated learning algorithms, and they also enter into the statistical properties. So how far is the learned parameter vector that I learn by solving GTV minimization, how far is this away from the true parameter vector? So this is related, this is called an estimation error. And we, in the lecture notes, you find bounds on this estimation error, so true underlying parameter vector minus the estimated parameter or learned parameter vector, and then you get a typically long bound, long expression, complicated expression, or not so complicated. But the important thing is that in this bound, the local data sets enter via the eigenvalues of this matrix Q. So why do I now tell you all this? Well, once you have a nonlinear model, what will be different is that this loss function, so we evaluate the quality of a weight vector using the loss function. And it turns out that this Q matrix here is the Hessian of this loss matrix for linear models. So when you have nonlinear models, you need to compute the Hessian, and the Hessian is then not given as this nice quadratic form using the feature matrices, but something else. But you can compute the Hessian using numerical approximation. So roughly, it's a very rough direction. You can generalize the analysis, or you can start the generalization of all this analysis in the lecture notes to nonlinear models by trying to replace, whenever you find this matrix here, this matrix Q, replace it with the Hessian of the loss function. And I just looked around a bit, of course. What is a nonlinear model that is currently very popular and media hyped? A deep neural network structure that you hear about a lot in the media. What is used in chat GPT? What structure? Transformer networks. So let's see if we are lucky. Hessian properties of transformer networks. Of course, I have tested this stunt before. So yeah, there's a recent paper. Why transformers need a Hessian perspective. So Hessian doesn't mean it comes from the state in Germany, but the Hessian is the Hessian matrix. These are the second order derivatives organized into a matrix of the loss function. And this paper seems to try to, yeah, here is the definition. These are the mixed partial derivatives of the loss function. And if you use as loss function the squared error loss and the linear model, you obtain what you get out of this Hessian is exactly the Q matrix. This feature matrix transposed times feature matrix. So for the linear model, this Hessian reduces to this Q matrix that I use in the bounds. And it seems they provide some kind of characterization for these eigenvalues. I didn't read it in detail, but this would be one direction. But this is hard. So this is, I would say, clearly beyond the scope of a typical master level course. But yeah, maybe if you're interested, I'm always all ears if you want to pursue this in a research project, and maybe we make a nice paper then out of it. Okay, any questions at this point? So one way to generalize all this analysis in the lecture notes, which is deliberately focused on linear models, because you get somewhat manageable expressions. So let me see one example for this analysis. One example, where did I, here in the federated learning principle, when I present upper bounds. Yeah, here, for example. Oh no, here's no, this is too simple. I avoided here the estimation error for some reason. Lambda 2, where do I get this lambda 2? Lambda x. Yeah, I think for the gradient methods, when I analyze the gradient methods for GTV minimization, here we have the, yeah, here. Here, all kinds of eigenvalues, different types of or different choices or different eigenvalues that are used of these Q matrices. So to generalize all this analysis, which strictly speaking only applies to linear models, you have to replace this Q matrix by the Hessian. And but the Hessian of a transformer network is a matrix of size, number of parameters, tunable parameters. So roughly how many tunable parameters do you have in a modern deep neural network? Millions or billions. So this is highly non-trivial how to characterize the eigenvalues of such large matrices. I guess you need to kind of pull all kinds of mathematical tricks, which are, as I said, clearly beyond the scope of this course. Yes. Any questions? If not, then